Good morning, all. My presentation is titled Make Your Code Fly at Transonic Speed. So this is about a very new package. It's a project we started this year. And I should also thank my current employer, Stockholm University, for letting me come here. So we are a team of researchers. Myself, my name is Ashwin. I'm a postdoc right now. And my team members, the team which are behind this project Transonic, there is Pierre Blanc-Fatin and Pierre Augier from Grenoble. Our main research focus is computational fluid dynamics, so we do flow simulations. So throughout the process of my PhD, we were developing Python-oriented packages for doing simulations, experiments, image processing, and this Transonic was the final leg of the journey. It was a spin-off project, but it's more general, so it might be interesting to you. So a quick show of hands. Who here uses NumPy a lot or thinks that their code is running really slow, uses a lot? So this talk is probably meant for all of you, but who hasn't, it's probably insightful as well. A short version of this talk would be, I'll be covering 3 aspects. The first thing is whether, when, or how to optimize your code. There are many solutions I will show. I did a quick survey of it. It's a lot. You will be confused by which one to choose. And finally, I'll show what Transonic is trying to do. It's a pure Python packages. It's meant to be a unifying front end for generating efficient Python code or efficient code. So you might be wondering, is it really that important? So Python's one of the strong suits is it allows you to rapidly prototype. So maybe it avoids scenarios like you are waiting for compiling for your small change in the code just to get it running. But at the same time, a trade-off was made, which is it starts to get slower as your problem size grows bigger. And even PyPy project commented that the more you gaze into the benchmarking abyss, the more it gazes back. So it's a dark hole. Starting off with something very general, this is like a guideline for all of you, how to write optimized as well as maintainable Python code. So Python's strong decisions that they made in the beginning is this emphasis on readability. So it's very easy to communicate algorithms. It's very easy to maintain them for generations ahead, but it came at a cost of performance. But typically, you don't usually need to optimize everything. As Donald Knuth said, premature optimization is the root of all evil. And real-world problems don't need you to optimize the whole code, as also our previous speaker was saying. One of the first things you should check is your problem CPU bound or IO bound? Is most of the runtime spent at the CPU or spending at communications? So typical example is for CPU-bound problems are linear algebra, differentiation, calculus, etc., which is a lot of data science and scientific computing. And for IO-bound, you have network communications, web development. So if it's CPU-bound, this is what we are focusing on. And you should not follow your gut feeling. You should do profiling. Python comes with a good standard C profiler, which would tell you how much time is spent for each function per call and in cumulative for the whole run. And before you even start optimization, you should check whether there are better algorithms, like our previous speaker was saying, and try to use better data structures. Maybe that would help for certain problems of bigger size. And always write unit tests, so you are sure that your solution stays the same. So there are 2 different pathways you can go with optimization. You can see whether there are existing C, C++, or Fortran libraries. And if they have already solved the problem for you, Python is good in talking to these languages. You can interface them. And even interfacing can be done in two ways. You can write it in another language like Py/11 or PyOxidize for Rust. And there were some older or even currently maintained ones like Boost Python and Swig, etc. Or you can go for a Pythonic approach. You write your code in a slightly Pythonic way. It looks like C, it looks like Python as well. But you will be able to communicate like Python if you want extensions, or if you want something interpreted, you can go for C types or CFFI. So that's interfacing. But this talk is not about that. This is about extending your code. So your problem is not solved by an existing library. You have to implement it yourself. What would you do? You can write your Python code, make it go faster. You can compile it ahead of time. You generate a dynamically importable binary, a C extension, a Python extension. Very popular libraries for that is Python and also Python nowadays. Also, you can do a JIT compile version, which for that NumPy is a good solution. This is a small example. Like this was the solver that we are developing for my research. It was called FluidSim, where we took both of these. We had almost greater than 97% of the runtime was spent in compile part. We used interfacing with FFT libraries, and we also extended the code with extensions. Now, you can also look at it from a software perspective. How much would you be willing to optimize? You can optimize the whole code, like Nutka was doing. It compiles the whole Python program into a C. Or you can swap an interpreter, for which PyPy is really good at optimizing slow loops. But PyPy comes at a drawback. When you're dealing with packages like NumPy, PyPy is not able, because of how CPython is made, it cannot look into what NumPy is doing behind the scenes, and it cannot optimize it. So it only works when you're dealing with mostly pure Python code. And then instead of doing the whole optimization, you can pick certain modules you want to optimize. Like Scythe and Python, they optimize per module. Or you can optimize certain functions or methods. NumPy allows that. And Transonic, the project which I'm introducing, it also allows that. And you can also optimize certain code snippets, expressions, and functions. So that was the NumPy approach. You just optimize certain functions, but the speed of the whole expression that you build out of NumPy is not optimized. It goes back to the Python world again, and then there is an overhead. This strategy was really successful, and this is the main reason why this Python scientific stack exists as today. So you have Python as a base, and NumPy, even NumPy uses parts of Python to build some of their modules. And it gives rise to several domain-specific libraries, which either was interfacing or extending the game. But it also means, as a developer, you're faced with several choices. So I was doing a survey of, there is a typo over there, but don't mind that. So as you can see, there is a lot of packages, a lot of frameworks that you can target. Most of them target C++ or C. And there are some emerging ones with which you can run your program in Julia, Rust, or Fortran. But it will be too much for this talk to focus all of those. So I limit our focus to what Transonic is trying to do. Transonic currently supports Python, Python, and NumPy. So, which begs the question, what is Transonic all about? Transonic is a word play because of our fluid mechanics background. It means that you are really close to the speed of sound, and the speed of sound is analogy for the C-like speed. It's a pure Python packages. What it does is it analyzes the Python code in the form of abstract syntax tree. It does not import it. It analyzes it. And then using a package called Benigit, which Python also uses, it generates some code for you. And this code would be compatible by Python, Python, and NumPy at varying degrees. Possibly more libraries would follow in the future. Your code is still Python-like, so you're not locked down into using Python or any of those. You can always go back and run it in Python to check for correctness. You can easily mix code. So if you remember earlier, I said Python and Python compiles it at module level, which means that your code starts having modules just to compile that small functions. But with Transonic, you can just add a decorator, and that would generate the Python and Python modules for you. You can even do it ahead of time, just in time, even for packages like Python, which does not support ahead of time. We have a just-in-time mode. This is mentioned earlier. It accelerates functions, methods, etc. Some examples, I try to be very simple here. Here is an example where you have a very Python-like code which runs well in Python. We add some decorators which are part of Transonic, which specifies the types that the function expects. Now the types, you see the type hints are in strings because NumPy has not yet standardized their form of type hints. So we had to invent our own. You can write it in a NumPy-like vectorized fashion or in a loop way. And when you do it in loops, you have to mention the types for the local variables only for Python, because Python expects that to achieve the full performance. If you're using other things, you don't need those, like NumPy or Python. How does it work? You take that code. You can generate the ahead of time extension either by using setup tools, or you can do it when you're developing. You use the command line tool. And then what it does is it generates some source code, which could be then compiled by Python and so on. You can also do it in a just-in-time way. And in just-in-time, the advantage is you don't have to specify those type hints anymore. And the types would be inferred during runtime. It will look at what values they are getting, and then it generates it for you. So, and while the compilation is going on, and Python takes somewhat long time to compile, it wouldn't wait for the compilation to finish. It uses the existing Python code to finish the job. And later on, when the compilation is done, it uses the more efficient code, and it'll run faster. Type annotations can be really simple, like you use built-in data types, int, float, etc. Or you can build your own. And this is how you can achieve overloading or polymorphism with Transonic. You don't have to rewrite the code for different data types or shapes of your array. You can do it with one code itself. Python also supports inline functions. Inline functions are comparable to the C inline, which are somewhat faster. So we have a keyword argument at boost inline equal to true, and that will be an inline function for Python. And on the right-hand side, you can see the generated code. As you can see, like when you have to write Python code, you will have to end up writing some boilerplate code, which is avoided by Transonic. You can even accelerate methods of classes, even when Python by design does not support classes. So this is really good. But it does come with some restrictions. The methods have to be quite simple, as in the method should not call another method. Or another example is you should not initialize an attribute of a class within this compiled method. You can also effortlessly benchmark your code with different targets. So here is a very simple example of a rotation operator in linear algebra, which rotates a bunch of points with a specified angle. And then you keep that same Python code. You can even generate an aliased Python or NumPy versions of it. And then what you can, Transonic comes with some utilities. It prints out the versions of your backends which are available. And then you run it once so that it warms up, it compiles, and then you can have this wait for all extensions function, which is kind of a lock. It does not allow the code to progress until the compilation is done. And then once this is done, you can run your benchmarks, and you can see what kind of speeds that you get with NumPy or Python. Python is quite good at keeping your code like a NumPy vectorized version. You don't have to write for loops. But in our experience, if you want to use Python or NumPy, you will have to rewrite your NumPy code with for loops. So to summarize, Transonic is not another accelerator to add to the problem. We are trying to address some of the problems, which is these accelerators that are there have incompatible syntaxes, and we are trying to unify them. And there is a dominance of Python right now. We are trying to give library developers more options than Python without worrying about compatibility. And Python could be more used in certain use cases, and it's not right now. This was just a glimpse of the whole performance landscape, as I like to call it. There is also the possibility that maybe your problem can be parallelized and made to go faster. You can do fine-grained parallelism when you break down your problem by yourself and do the parallelization, or you can use pre-existing data structures like PyTorch or Dask, which would be parallelized by default, and then it would do the parallelization. But there's another problem which is going on, like NumPy arrays are not compatible with these, and there is ongoing work to unify it. Maybe Transonic could be part of the solution, but it's not maybe in the distant future. So thank you all for your attentions. All the slides are online. You can access them in that link. And there is a demo, a binder demo, if you want to try Transonic right now without installing it. So thank you.
Stand the speaker. Thank you. Fantastic responsibility towards lunchtime. We have plenty of time for questions.
Hey, thanks for the presentation.
Thank you.
Maybe first of all, I think it's outrageous that you're from Fluid Dynamics and didn't put any beautiful graphs.
I should have.
But yeah, I wanted to ask. You guys are working with CFD, right?
Yes.
So I kind of can guess the reasoning behind building something like this. But if you're like dealing with PDE simulation, you have tons of libraries these days, like Firedrake, Phoenix, etc., for fluid dynamics. So maybe give your use case. Like, why did you build this?
Why? Yeah, I had this question in my defense, actually. So when I started out, so even when you're solving PDEs, there are different methods. So Phoenix uses finite element methods, which is not what we want. We want something really accurate with Fourier transform-like precision. That method is called pseudospectral methods. And for pseudospectral methods in specific, and from a Python approach, there were no packages when I started my PhD. But there is now, like there is one which we built, And at the same time, other researchers, one from Norway, one from US, were building similar ones, which are now available. So now you don't need to build them. Yeah. So it was just not there when I wanted it. Thank you.
More questions, please. I especially like that comment about the beautiful CFD figures.
Yeah.
I really appreciate that too. I mean, it takes, it's really hard not to include one.
I'll update the blog post with some videos.
So, if there are no questions, let's thank Ashwin again.
Thank you.
And here's your diploma. Thanks for coming.